Test. Wygląda na to, że działa. Dobra, to może się rozwiązać. Dobra, no to jak coś to... Dobra. No to cześć.
Yes, so I asked him if I can use that one.
Yes.
Tak. Preferuję mikrofon. Dobra.
Test.
Okay.
Good stuff. Okay, I think we can start. So for today's keynote, we host Emily Ishida with her talk From Theory to Practice, How Python Enabled Modern Astronomical Data Analysis. Please give a warm welcome.
Hi, everyone. Can everyone hear me? Yes. Okay, perfect. First of all, I'm super happy to be here. I would like to thank the organizers for inviting me. This is my first time in this conference, so I'm very honored to be here. A little bit, since this is my first time, and I don't think so many of you know about me. I am originally Brazilian, but I'm based in France, in Clermont-Ferrand, which is geometrically in the middle of France. I work mostly on applications of machine learning with astronomy in the context of developing interdisciplinary science. And when I say developing, I mean the sociological part of what it takes to develop interdisciplinary science. So I have to give some warnings. I am not at all a programmer. I am completely out of my depth here, so be nice, okay? Okay, good. So just before I start, just so I can fill the room, are there astronomers here? Anyone? Okay, okay. So, so I don't have to change my talk too much. I hope my idea today here is more than talk about the techniques, to try to go back in history a little bit and try to understand how modern observational astronomy arrived at the moment as we are right now, and what are the challenges that we have to do in the future, and why the community as a whole has decided that Python is a good tool to guide us through this journey. So more or less what I'm going to talk to you about today is I need to do a little bit of introduction, so there's going to be a little bit of astronomical definitions. I'm going to describe a little bit of the first initiatives on Python. The arrival of large-scale sky surveys, I will explain what that means later. And what does this mean for discovery in astronomy, which today is very, very different from when the field started, and what we can do after that. Before I say anything, I have to say that I have 3 kids. These are my 3 kids. And they are all in different results of different co-parenting situations. So for myself, it's very difficult to understand what exactly are my contributions to these projects, because these are amazing people with whom I learn a lot. So everything that you like in this talk is their work. Everything that is wrong is on me. That is absurdly sure. Normally, I tell them that my biggest contribution to the projects is to remind them that deadlines are coming. But okay, how did we get here? We have to remember that astronomy, from the moment of the invention of the telescope, so before the telescope, it could be a social event. But from the moment that you invented the telescope, astronomy has been traditionally a very, very solitary experience. A telescope has never been something cheap to have. It was very difficult access. Normally, you would have one telescope in the backyard of a very rich guy. And the astronomer would be there. The first telescopes you couldn't move, so you had the telescope was like fixed in a direction, and the sky would move in the background. So traditionally, this developed in the community a very personal relationship with their own data, because since this is an observational science, the table only, no matter how good a note-taker I am, the table will only tell me half of the story, because it depends on the sky conditions on that day or what happens to the telescope. And that would be very, very particular to each observer. Those telescopes that were in the backyard of a very rich person normally had a resident astronomer who would spend winter nights outside observing, and during the day he had to teach because he needed to make money, and then he died of 32 of pneumonia. These are the story of all of them. So in this context, all of the tools were developed very specific. These started there, but if we go forward to the end of the 20th century, things still kept something of that. Each task, each thing that you want to do was separated in many different tools. So in the end of the 20th century, you would have these super powerful tools that would be separated for individual tasks. So for example, individual niche of astronomy, or a given wavelength range, for example. For my case, I started my academic career doing supernova cosmology. So yes, my first code was in Mathematica, because it was very, very, very analytical. And even later, you can find, today you can still find a lot of examples of blog posts and descriptions of people discussing between these tools. Should I use IDL or should I use Python, for example? This is something that you can still find very traces of. But when the data start becoming very big, the community did not have much option. Here we have to remember that the development of astronomical data is not linear and it's not smooth. One telescope is something that takes a long time to build, so you have like 20, 30 years between one generation of telescope and the other generation of telescope. So the data comes and it does not want to know if you are ready for it or not, right? And there are no such things as benchmarks, because each telescope is completely different from the other one. The Sloan Digital Size Survey is probably the most, one of the biggest examples of this. If you like history of astronomy, there is a very nice book called A Grand and Bold Thing, and it describes the history of them building the telescope and trying to put the telescope in operation. There's some very disheartening scenes where after all of the effort that they made, they are unable to point the telescope where they want to point, which are things that happen. But this is, Sloan is still working, 2.5 meter telescope. It has a multi-CCD camera and a multi-object spectrograph. And at that time, in 2000, hundreds of gigabytes of raw data per night was unprecedented. It was like a lot for them to deal with. And these made kind of the community start to talking about those things. You probably heard about AstroPy, and you know about this much more than I do. This is from, I took this from a slide of Eric Toledo in a Python in Astronomy conference that I went in 2015, more than 10 years ago. And so if you want to do something very simple, like convert equatorial to galactic coordinates in 2011, you have all of these options of how to do it, and most of them don't talk to each other. And the question at the time was, do we as a community really need yet another separate Python library for astronomy and yet another attempt to build on top of previous IDL libraries and things like that? And the AstroPy actually was built from a need from the community that decided that this was a good thing to have. It was officially released in 2013, so it has, when I describe AstroPy, I say it does for me all the things that I once knew, but I am very happy to forget how to do. Because in astronomy, positions and velocities and distances are things absurdly complicated because the Earth is moving. So suppose that you have a point there and you have a picture and you want to show someone that picture and you say, please look, the picture is there. But this person is moving, right? All the time. And not only moving around themselves. So the Earth moves around itself, around the sun, and the sun moves around. It's a mess. So AstroPy is really, really, really powerful and allow the community to have homogeneous way to do this, which is super nice. It's an amazing work. In 13 years, it has like more than 1,000 citations a year, which is, for us, it's a very big thing. But this was just one effort. A lot of efforts have been made in the same direction for the other tools, and all of them trying to bring them together to the Python community. I asked before this talk, in preparing for this talk, I asked all my friends who understand this much better than me, why Python? Why didn't you go to Perl or, I don't know, something else? And one thing that there was the expected answers. They said it was elegant, it was relatively fast, it is easy to connect with legacy languages, which is true. But I think the most interesting thing is that it's not even that it's friendly, it's that it's not scary. You see, like when I look at a C code, even if the important thing for the newcomer is to build the belief that you can learn. And I think Python tools are very, very successful in doing that. Okay, so so remember, AstroPy was 2013. In the meantime, what I was doing, as I told you, I started in Mathematica, so it was super analytical work. Coin, which is my eldest child, is from 2014, so it has 12 years now. And the idea of Coin is collaboration per collaboration. We can talk more about this if you want afterwards, but the idea of Coin is to foster scientific collaboration as an end in itself. The project will not matter as long as we want to share the experience of collaborating in something with people from different areas. And astronomy is just nice because it's easy to convince people from random places to collaborate with you most of the time. It's called Cosmostatistics because our initial idea was n-body simulation. So we started using a lot of GMMs and stuff like that. And because of that, we attracted a lot of statisticians. So there's still a huge fight between R and Python. And I was in charge of one of the Python packages in the first coin residence program that we made. In April 2000, so the meeting happened in August 2014. And in April 2015, which is the same Python in astronomy that when I saw the slides on the AstroPy that I told you about, I built my first Python package. And beating me, this is amazing. A tool that allows me to do that is really, 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 really powerful. Don't look at the code. It's just like historically nice. I'm proud that I did that at some point, but yeah, it's done. So that was 2010. So what happened since then? As I told you, data in astronomy comes in waves. So we have the slow one, which is 120 terabytes of data per night. The Zwick Transient Facility is something that started in 2018, and it's a survey that is still ongoing. It's generating 1.4 terabytes per night. And the Vera Rubin Observatory, which started a few weeks ago, is expected to produce 15 terabytes per night. This data is being delivered to a community who can still, up to this day, write a 20 pages paper about one object. Right? And this is the data that we are delivering to them. So now I have to explain to you something very important about the data in astronomy. There are two types of observations. You can get photometry, which is a picture, right? So you take the telescope, you put a filter, so here you see a few different filters on top of the telescope. You open for a few seconds, you close, you have a picture of the field of view of the sky. And this picture allows you to measure the brightness of each point of each pixel in that picture. This is photometry. On the other hand, you have spectroscopy. So suppose that you took your telescope and you opened the telescope, took a picture, and then afterwards you went to the mechanical shop and made one physical hole in every galaxy where you want a spectra, which is light as a function of wavelength, right? So you want a very, very high-resolution observation. Then someone, for slow one, someone went there with the hand and put optic fiber in each one of the holes where you want a nice spectra for. All of this has to be mounted on top of the telescope You point where you want to point exactly correctly, and you integrate for at least an hour. So the difference between now is that you don't have to manually put the optic fibers there. Now you have robots that put the optic fiber there for you, but the idea is the same. The different types of data that you get with this thing is for photometry, you get what we can get pictures. So for example, here you see a galaxy, for example. Or if you point for the same point of the sky many times, you get a light curve, which is brightness as a function of time. I am a supernova person. I'm going to talk to you about transients, so we are going to talk about light curves a lot. This tells you how that the brightness of that object evolved with time, okay? But if you take a spectra, for each point where you took a spectra, you will have a detailed description of that light as a function of wavelength, and then you can identify, for example, if there is hydrogen or not, if there is helium or not, and then you can have a real astrophysical description of the object based on the chemical elements that you can identify. Obviously, this is widely available. You integrate, the field of view is huge. You can take pictures of the entire sky in a few days with Rubin, for example. This is very rare and very expensive. Obviously, these are features, these are labels, and this is not going to change. So, when you talk about these, and I tell you about all of these big numbers are all photometry. So you have a lot of features, but you not necessarily know what you are looking at. It can be any type of supernova, it can be different types of galaxies, it can be any type of star, and you will only have, most of the times you will only be sure about that if you can take a spectra, which you cannot. So, for example, one of the things that are done with this, so this is, you probably heard about dark energy, which is the thing that is the universe is expanding in an accelerated manner. And the way that we came to that conclusion is by studying Type 1a supernovae. So you have to first something explode in the sky. You have to take a spectra to know if that thing is a Type 1a supernova, which is basically the explosion that involves a white dwarf. If you know that is a Type 1a supernova, then you are going to follow that object and understand the shape of the light curve. So you can understand the brightness at the peak of the light curve and put in this plot. And I'm not sure if you can see, but there are different dashed lines in the end of this plot. And between these lines, you are going from a flat universe with no matter for a flat universe completely dominated by something else. And this is the size of things that they want to understand. This was the Nobel Prize of 2011, by the way. They won the Nobel Prize with 42 points. So this was one of the first arguments for, okay, let's get more data. So we are going to build these very big telescopes. And very soon people realized that you could not do that by hand. You cannot classify these things by hand. So in 2010, there was the first data challenge. It was called Supernova Photometric Classification Challenge. And it was a simulation of different types of supernovae. And there was like, I think, 18 or 16 different entries that were submitted. This was so in the beginning of things that I highlighted for you the 4 that I could identify as machine learning based. All of the others were more like statistical light curve fitting or like some analysis that they were already used to do with their tools, but obviously could not scale. So at this point, we arrive at the large-scale surveys, and it's obvious that machine learning is unavoidable. And this was a huge fight. Like, a lot of people, this is still very skeptical. For some cases, I am too. But for all that matters, machine learning is unavoidable. So what you have to keep in mind, data is not ideal. These are inhomogeneously sampled, noisy, multidimensional light curves, which make all of the statistics you know for the treatment of light curves useless because they are not homogeneously sampled. There are no benchmarks, and representativity is not possible. Labels are absurdly expensive, and this is not going to change. So 8 years later, there was another So obviously, this fomented a lot of development on the machine learning side. So people said, we can simulate, so let's simulate a lot of data. and we are going to know how it behaves. So in 2018, I think it was 2018, yes, we made the plastic, which is photometric LSST astronomical time series classification challenge, and I did not make the acronym. So it was very important. So the majority of entries, so we see you have more than 1,000 teams participating on this. And majority of the entries that we received was very heavy-based deep learning methods. The person who won used boosted decision trees with scikit-learn and a very, very, very clever pre-processing, which is something that you should keep in mind with astronomical data. The data is terrible. So even if you have a super perfect machine learning model, the huge impact will be on the pre-processing that you are able to do because you understand the data and you understand your telescope and you understand the astrophysical processes that is going on. In this sense, there has been a lot of development starting in Python, and now there is a lot of Rust also in the middle of this. But the light curve package was developed to enable like a homogeneous sampled homogeneous way to extract features. It can be a statistical feature, so you have those super horrible light curves, you take things like mean, standard deviation, blah, 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 and you invent your statistical features. It can be machine learning embeddings, so it can be abstract things that come from deep learning models or other things. So all of this is a way to homogenize the data in a way that it makes sense before going to your machine learning data. And obviously, there are a lot of deep learning. Another caveat, I am not a deep learning person. I don't understand it completely. I just know that a lot of the deep learning efforts that has been developing in this field is based on Python tools too. What is more important is what if you want to use real data? Because everything I told you about up to now was using simulations, right? So simulations are good, but we only put on the simulations what we know. If you knew everything, you didn't need to build a telescope, right? So by intrinsically, there is something in the real data that there is not in the simulation, otherwise there was no point of doing all this. So if you want to do it in real data, then you have to be clever on where you put your efforts to get labels. And this is active learning, which is like, it has many different names and many different approaches, but the main thing is you start with a super small and bad training sample, you train a machine learning model, and then the code itself tells you, for this specific object, I don't have the label, but it would be very informative to my model in case I had the label. And then you send that to a person. That person is going to remember, go there, take a spectra, reduce the spectra, blah, 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 blah. And then once you have a label, you put it back and you train it again. There is it's a little bit of effort, but very soon you arrive of an optimal way of not wasting labeling resources on things that you already know, so you only label things that's going to be useful for your model. And this was my second Python package. This one is still maintained, so this one, if you want to look, you can still look. So this was the plot only shows you the difference between the blue is when you make an active decision. In this case, it was just uncertainty sampling. So at each loop, I would get the label for the object whose probability was close to 50%. Because that means that the model doesn't know anything about that object. And then you do that many times. Passive learning is random sampling, so I don't make a decision, I just go there and take a random label. And the canonical strategy is what happens if you keep labeling things that look like type 1a supernova. Because talking with the astronomer who sit on the telescope, many of them told me a spectroscopic time is something very, very expensive. So if they see something that is going up, it's kind of blue, 3 points in a light curve, they know is a type 1a supernova, they will take a spectra because they know it's going to be useful for cosmology. From the machine learning point of view, if you look at 3 points and you know it's a 1a, I don't need a spectra. I need a spectra for the other things. So in the red case, you keep adding data to your model, but you don't add information, so the classification doesn't evolve. So, and then if only and then you plan your observations, you collect more data, you analyze more data, and the conclusion that you get is that you need better data. And then you build a new telescope. But since this is an observational science, you build a new telescope and you observe, but when you observe, you are not going to observe only the thing you want. You are going to observe everything that happens in the vicinity, and then you find more problems. This is an infinite loop that, fortunately or not, this is how it works. So, and this is how discoveries in astronomy work for many times. So this is how you find the unexpected. So we have examples, for example, of Galileo Galilei in 1610 finding the moons of Jupiter. And if you can see here, he is asking why these 3 dots at some point is from one side of the planet and the other point is from the other side of the planet. And he was trying to understand the dynamics of it, but he was not planning this. He just observed and appeared. Or, for example, the cosmic microwave background radiation that the guys built this antenna. They thought it was noise. They was trying to clean it up. It was not. It was signal from the cosmic microwave background radiation. And there was another group that was actually in the process of constructing an experiment to measure that, but the Nobel Prize went to the first guys anyway. But in any case, they were not expecting, and this appeared in their data. And if you go a little bit more on the transient side, we have the comet over Prague in 1577. That was the spike for many of the observations that Tycho Brahe did over his life. All of these more or less fit the profile that I told you before. And in this sense, we have to keep in mind that if you build a telescope, you are taking the largest camera ever built, right? And you are looking somewhere where nobody have ever seen, because the camera is bigger, you see further away. So you are probing a time on the evolution of the universe that nobody have ever seen before. You have to see something new. I really like this quote by Norris from 2017 that says that telescopes that merely achieve their stated science goals have probably failed to capture the most important scientific discoveries available to them. Because when you build a telescope, when you ask money to build a telescope, you have to make a scientific proposal based on what you know, and that's the best that you can do at that moment. By the end of the life of the telescope, you have to have found something unexpected. But the problem is that now that we are receiving 10 million things and 15 terabytes of data of night, serendipity was lost. You are not going to find things if you're not looking for it, right? So we have to find a way of finding things that we don't know what they are exactly, because you know they are there. They have to be there by definition. And now it's data mining. So, for example, and obviously in machine learning language, this becomes anomaly detection. So, for example, the Zurich Transit Facility ZTF that I told you a little bit here, data release 3 had about 2.25 million objects in this field. So I'm not talking about the entire sky. We only took the fields that are highlighted in the image. And the anomaly detection part, I have to say, is my middle child. If I don't mention all of them, they get angry. What is happening? So remember that anomalies, in order for you to define an anomaly, first you have to understand what is normal, right? So in this specific data set, the normal was variable things that repeat, right? So not things that fade away, not transient. So variable things that keep repeating, or even if they don't repeat, at least they don't disappear. So this is what you would consider normal in this situation. So we just did very simple feature extraction with the light curve package, as I told you before, a few scikit-learn anomaly detection algorithms in 2.25 million objects. And I had people looking through 277 of them. They found a lot of things. I am not going to describe this because I don't understand half of what is written on this slide. But the one thing that is important for you to remember is that those are rare. This thing here that I don't know how to read. But the most important thing for us here is that 68%, almost 70% of what they found was artifacts, meaning The telescope moved. There was a satellite that passed in front of the camera. There was a bad CCD. Something happened. The algorithm is correct because statistically they are anomalous, right? But this is not scientifically interesting. So what we have now is to find a way to automatically identify what we call anomalies and what we call outliers. For the sake of this talk, inside SNAD, what we use is that anomalies are things that are scientifically interesting to the expert, whoever the expert is, and outliers are things that are like bad CCDs or things like that, or maybe an alien passing in front of the telescope, but we cannot know at this point. So we have to identify these things. And for that, we can also use something that is close to active learning, because you see, the experts don't know now what they are looking for. So what we are going to do here, we are going to start with a normal isolation forest, very simple. You just take this data and in this very big dimensional space and ask, get me the object which is furthest away from everyone else, right? So you have this distance in this parameter space, and you take the objects which is with the highest anomaly score, so which is further away from everybody else. You send it to a human and you ask, is this interesting? Do you want to see more of this or not? If the human says yes, nothing changes. You go to the second object of the list because the model is correct. If the human says, no, I do not want to see this, this is not interesting to me, you go back to your machine learning model and you change the parameters of the model in order to comply with the definition of the expert. In this case, the only thing that the expert needs to know if is yes or no. And the expert will, with the time, construct their own definition of anomaly, even if they don't have a mathematical description for that yet. So we did that in that data set. And in this case, we said to the expert, OK, say yes every time that something that looks like a supernova appears, which is something that goes up and dies. Because remember, the default of that data set was something that repeats and stays on. By the time the paper was written, we found 104 things that look like supernovae, and 47 that has been missed by other searches that was done before. And just a reminder that all of these should have been gone through a different pipeline, because transients is a different pipeline. That's why people were not super enthusiastic when we decided to start this. Nowadays, all of this is in this NAD catalog, and nowadays I just counted, we have like 200, almost 280 new transients that were found with different algorithms in the same way. But then I know my time is almost up, so what I have to do here is to remind you that there is a huge infrastructure that is necessary in order to make this happen. The SNAD viewer is something that was developed for ZTF because in the beginning, so the difference of this it's not all of the people who are answering this, they are experts on that specific field, meaning they are very detailed. So you show a light curve in an object and you ask, is this interesting or not? And they take 3 days to answer yes or no. Right? So the viewer was something, it's a website that gathers together a lot of data related from transients in order to make sure that this reply for the expert is faster. There is problems, obviously. The algorithm, the specific algorithm that we were doing is very expensive. So there was a new implementation that was also developed. The backend is mostly in Rust at this moment, but the whole tree construction, we used scikit-learn for a very long time, but very recently, the whole tree construction thing was done in Rust. And there is a whole infrastructure that allows you to automatically prompt the user with this link. And every time the user has to answer yes or no, it goes to the viewer, which is a website with a lot of information from the same object to allow the user to say yes or no quickly from all of this. And all of this infrastructure needed to be developed. So finally, what is going on now? Remember that everything I showed you up to now is on data releases, means static data. We still have the people searching for super fast things that needs to be done overnight. So what we have is a model that is the same thing. It starts with isolation forest, and at the beginning I send 10 candidates every day for people because I thought that was nice. As I told you before, it was not. After a week, they don't look anymore. But the way, and remember, the expert here has no obligation to know nothing about programming or machine learning. They need to know astrophysics because we are really in need of people who really understand the astrophysics of the thing. So we deliver this to their cell phone. So this is a Telegram application, can be Slack, can be WhatsApp, can be whatever you want. In this case, they chose Telegram. So every day you get on real time 10 different candidates. And since it is Telegram, you can react, right? Say I like it, I don't like it. You do it like this, and then the model is retrained, and with time you improve the definition, and hopefully you are gonna start receiving things as you like. With the first try that we did for this. So we have this channel here that if you scan the QR code, you can go to the Telegram chat. This is what we called group replies. So there are like 30 people in this thing, and everyone can reply. And then we made an analysis. What we learned from this? First, people get bored very easily. I already told you that. Second, these two histograms showed the classes that people decide are anomalies and the classes that people decide are not anomalies. And if you look at the labels, they are exactly the same. Why? Because I have 30 people in this group. I have a bunch of supernova people, a bunch of asteroid people, a bunch of variable star people, and the only thing that we did was we do majority voting. So if more people say yes, it says yes, and if more people say no, it says no, and the model doesn't evolve, basically, because they don't agree between themselves. So what we are working on right now, this is not released yet, but this is what it's going to be done very soon, is that for individual users, you will have your individual channel. So only you can react to your answers. And then there is the whole sociological problem of making humans being consistent on the answers that they give, because also after a while, their definition of what is interesting or what is not changes, and this is a whole other problem. But this entire infrastructure allows the user to have this personalized space, for example, where they can change their minds, they can ask for the model to be retrained and things like that. So, take-home message, what I want you to remember from all this. Anomaly discovery is a highly human-centric corner of machine learning in this type of scenario, because you do need a human to look at this. The challenge here is to match experts with unique data points. We had a very nice variable star discovery that was in the drawer for 3 years because we didn't have variable star people to look at it, and we didn't know it was important. The expert has no obligation to know anything about the machine learning or the algorithm they're using, but they do have to believe in you. Otherwise, they will not do it. And the most interesting discoveries happen when the expert does not have a clear idea of what they are looking for, but they have some idea. They can have a very broad idea, and we have to allow them to search in these conditions. And finally, human bias is a feature, not a bug. We want to input that into the data in this context. So what now? Where are we going from here? I think it's still very early to say how all of these new technologies that are appearing is going to impact all this. I have to tell you that there is a lot of effort being done within the astronomical community to develop, for example, large models that tokenize different variations of the data for the same objects in the hope that we can transfer expertise, for example, from one subdomain to the other. And we still have to understand how this will impact the field. What is certain? What we can be sure about? For classification, the future is photometric. That is no point of this, no point in discussing this. And the only thing that we have to do now is to build up the community trust on the automatic classifiers. I think the classifiers now are pretty good in comparison to what they were some time ago. But we still have to build a conversation with the users and with the community to make sure that they go to their full potential on the scientific results that they can have. For discovery, the main challenge is to match the correct data with the expert that can provide interpretation for this. New physics will be there. and maybe we will not see it because we don't know that it's there. It will be there for sure, I'm certain. But it would be very sad if we learned that they were there 10 years after the fact. But I want to finish in a positive note because I think that all of these is an opportunity because data in astronomy eventually becomes public. Like the protocol normally in astronomy is you build a telescope for a few years, not a lot, like 2, 3 years, 5 maximum. The data is proprietary. The data, I mean the images, okay? The alerts for transients that I say is public from the start. But the data for the images become proprietary for a few years so the people who build the telescope can do something with the data. But after that, the data is public. So this is how it happens with most of the astronomical experiments. So the data is available and astronomers love to talk. So if you ask, they will be more than happy to open a conversation about what can be done with this data. And finally, what do I want you to remember if you have to forget everything that I said today? Modern astronomical data analysis, everything that I said here is heavily dependent on Python tools because of all of the nice things that we already discussed, but I also think because of the community-driven aspect of how things are developed. And I think this is something that we should be very, 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 very careful to maintain. Readability is nowadays is much more important. Even if we have other tools, the fact that I can, with my not so deep understanding, read a code and understand what it's doing is very, at least psychologically calm for me. The community-driven aspect of all projects discussed here are the only thing that guaranteed that they will remain relevant regardless of what happened. So all of the things that I told you about are done bottom-up in the sense that every single button, every single feature was done because someone asked for it. I think what I want to say is that it's very important when you are doing fundamental science, to involve the domain expert in the beginning of the conversation when you are developing pipelines. Because this will not only allow you to develop something that you know is going to have some scientific output, but also will build the trust between these two communities and the next project will be easier. And I think Python is a very, very nice example of how that is done. Thank you very much.
So the questions?
Great talk, thank you. I was curious about the last bit about anomaly detection. When you send the anomalies to human experts, how much data would be necessary to automate or like predict the human expert's response? And are those humans worried about that?
So that depends a lot on the human. So all of these that I was telling here needs to be very personalized, because so the way that you should think about the way that is done right now, I can tell you what we did right now. We took, I think, 6 or 7 days of data, which is like a million points, a million light curves, from different parts of the year to make sure that we have like different weather conditions and things like that. And the initial model was trained with that, okay? And this is the initial model. In the beginning, you have to say no a lot, and that's where the people get tired. But after you say yes a few times, there is a parameter that you can control the impact of the response. So you can say, I never want to see something like this again, or lower the probability of showing me something like this again. So all of these are things that, talking with the user, you can like back and forth tailor to what they want. So in the end, each one is very different from the other. But I would say the minimum, I don't know, a couple of months maybe, you have to look at it.
With these anomalies, you mentioned satellites. Are you finding there's an increase in these anomalies due to debris and satellites as these things are increasing in number?
I'm being record, I think. So these, we try to remove those things before sending it to the model. So there is a few satellites that are known, so we can they are automatically removed. We have a few science modules of people who are actually looking for satellites or space debris. For the big space debris, there are catalogs of space debris, so we can predict where they are going to be. But most of the time, the user will have to deal with them but there is a lot. Answering to your question, yes, there is a lot. The amount of, I didn't told you here about the amount of pre-processing that is necessary before the difference imaging analysis technique, because all of that there's a huge treatment of these images that is done before sending it to us even, so.
Thank you, Emily, for the interesting talk. I have a question from one of your takeaway message. You said that expert intervention or expert bias is a feature, it's not a bug. So how do you include that in your anomaly detection?
Yes, so I think the way of including that, so there are two ways. First is the personalization of the models, right? And second is making whatever comes out of your module available to everyone. So the way that Think works, at least, is like this. So you build something, for example, you build a model. Your model has a very, very specific definition for your science case. But once your model is integrated to the broker, the output of your model is free for everybody to use. So you can take advantage of the efforts that other people already did. And I got asked sometimes if you're going to be scooped by other people or something like that. But there are not that many astronomers in the world, you know? It's a very small community. And when you make things open in this type of sense, you allow many people to take advantage of what others already did.
So you know about this Astrometrica, right?
What?
Astrometrica for asteroid detection. It's for open community for.
Yes, yes.
So do you have any plans of doing it?
Not me specifically, but maybe one of the other PIs have. I'm not going to answer that, but I can check and get back to you. Sorry.
Okay, last one.
Hi, it was a great talk. I just wanted to ask that before anomaly detection, you mentioned that there was some machine learning that was being done on the data. I want to ask what kind of machine learning was that, since you mentioned data comes in waves. So was it semi-supervised, supervised? How was that?
So, yes. So I think, yes, before the anomaly detection, what I was saying, I have to remember. Yeah. So most of these, yes, most of these are supervised, because they are done with simulations. So you have two options here. So you have two options. If you are going to use a very complex deep learning model, for example, or something that needs a lot of data for training, you need to go to simulations. There is no other option because there are no labels for people. There are also a few, I don't remember which is semi-supervised, which means that if you believe your classifier a lot, you use the high probability outputs as a label or something like that. So there are many different types of approaches. If you're going to do it with real data, then the model needs to be small because there's not many labels. But also in the real-time analysis, I think I'm afraid of saying the wrong number, but we receive something like 10,000 alerts per minute. So the processing needs to be very fast, and that actually constrains the size of the model, because you cannot take too long to process to infer the probabilities, for example, because otherwise you will have a backlog.
So, I mean, it might be a naive question in terms of astronomy, but how intense was the feature engineering that you have to do each time when you get new data?
So it's a very good question. So the feature engineering is decided at the training step. So we ourselves don't do the feature engineering. The science teams that are developing the models, they do the feature engineering. So what we have to do, what we tell them that it's very important to have a lot of selection cuts. Because if you know what you are looking for and you can put a lot of selection cuts, for example, I don't want anything that only has 1 point, right? So this already lowers a lot the burden on the feature extraction that is have to do. So before integrating the module to the broker, there is a lot of these tests that we do in order to make sure that it's going to be fulfilled.
Thank you once again.
Thank you.
Right, and now we have a coffee break. We see next talk in 20 minutes.
I had one question, if that's okay. So when you provide the informative, potentially, well, the anomalies for yes or no voting to the users, have you ever considered asking the users for more than just yes and no, but asking them which bits
and the other one.
Did you make some sort of announcement at break or something?
Sorry?
Did you make like some sort of announcement at break, or maybe just let people know as break is ending that there was a schedule? Yeah. Yeah. I'm not talking with the HTML. I'll explain that. Okay. I think we should give it a minute or so just to let people. Yeah. No, I have my own.
All right. Good morning, everyone. Thank you all for being here. For this talk, please give a warm welcome to Bryce Elstein-Lelbach on his talk on Python tile programming for GPUs.
Hi, everyone. I know there was a little schedule confusion because I had two talks and neither of them were supposed to be in this slot because they had a speaker who dropped out. So I'm going to do this talk now, and then I'll do the other talk later in the original slot when I was going to give this talk. So hopefully you all, hopefully this is the talk that you all came to the room for. If not, well, you'll learn something new. So my name is Bryce Elstein-Lelbach. I'm a principal engineer at NVIDIA, where I founded the CUDA Core Compute Libraries team, and I now lead the Vanguard programming group, which is responsible for programming language design and evolution. So my job is to make every major language a GPU language, from Fortran to C++ to Python to Rust to JavaScript. I'm involved in the leadership of many programming languages. I chaired the Standard C++ Library Evolution Group and the American Programming Languages Standards Committee. So today, I'm excited to share with you a new programming model and compiler stack for CUDA, which is Python first and Python native, CUDA Tile. But before we get into what CUTile is, let me explain why we built it. And let's start off by looking at the landscape, starting with the two existing GPU programming models. So the first is grid-wide programming, where you invoke individual parallel operations on the entire input, such as a sort or a scan. The algorithms are launched from the CPU. So you don't explicitly parallelize or partition the data. The system does this for you automatically, deciding how to divide up the problem and map it to execution resources on one or more GPUs. So this is the easiest and most common approach to GPU programming. There are many excellent GPU-accelerated libraries and frameworks that embody this grid-level programming model, such as CuPy, PyTorch, cuDF for data science, cuBLAS, cuFFT, and cub. So libraries should be the first thing that you reach for when you're writing GPU code, because they're going to make your life a lot easier, and they're often going to give you better performance because they're written and tuned by teams of experts. So you should try libraries before you write your own GPU kernels. For almost every use case that you can imagine, there is an existing library or framework, especially in Python. And if there is, then try it out and benchmark it. And if it delivers the performance that you need, then you should just use the library. Don't try to reinvent the wheel. However, sometimes there's no library that does what you need. Or you need to fuse different algorithms together in a unique way. or you've tested and found that you just can't get the performance that you need with libraries that do exist. Additionally, in the agentic age, I think there's a lot more value in writing a bespoke solution because it's a lot lower cost for you to do so. So agents are pretty good at going and writing custom kernel, custom GPU algorithms. So those are the cases when you should think about writing your own GPU kernel. A GPU kernel is just a function that is executed in parallel by a group of threads. All of those accelerated libraries are implemented with GPU kernels. Today, when you write a GPU kernel, you are programming at the thread level. You explicitly code every thread that you run on the GPU. So you decide how to split the compute work into blocks, how to divide the data into tiles, and how those blocks and tiles get mapped to threads. We call this programming model SIMP, and it's been the only way to write CUDA kernels for the last 20 years. So writing CUDA SIMP kernels gives you complete control. It allows you to program and tune every aspect of the GPU. And in each generation of NVIDIA GPUs, you expose more and more tools, giving you greater control and freedom. But all of these choices can be overwhelming. What we really need is a higher level abstraction that succinctly expresses the computation and allows the system to select the tools to implement those computations. So since Volta, which was 2017, NVIDIA GPUs have had tensor cores to accelerate operations like matrix multiplication and convolution. And in every GPU generation since they were released so Qtile C++ came out with the release of CUDA 13.3, and it works alongside the existing CUDA C++ SIMD programming model. So you can write tile and SIMD kernels in the same source file. It's compatible. And you'll be able to start adopting tile programming in your existing CUDA C++ code base. And you can now also use Qtile in Julia thanks to a community-driven project that's available on GitHub today. We've also recently announced Qtile Rust. So we've been exploring tile as a memory-safe way to write CUDA kernels in Rust. And the results there are very promising. And also more recently, NVIDIA's sort of committed to a long-term Rust strategy. So just as we've brought CUDA to Python, we're going to now also bring CUDA to Rust. So we're really thrilled about the growing Qtile language ecosystem. We're really excited to see where it will go next. And I've been surprised how easy it is to integrate into languages. Someone internally was experimenting with Haskell, Qtile for Haskell. We also sort of vibe coded this Qtile OCaml for a particular customer that was very excited about OCaml. And one of our product managers implemented Qtile Basic, which we released as an April Fool's joke. But it's funny, but it actually is like a real working example of how to build language support with Qtile. You can find it on GitHub today. It's honest to God, it works. All right, so now let's look at the tile programming model and contrast it with the traditional SIMD programming. So in SIMD, the unit of execution is a thread. You write kernel functions that are executed by many threads at once. The set of threads that a kernel runs on is called a thread grid, and this is hierarchical. It's organized into different subgroups of threads. You have warps of threads, you have blocks of warps, you have clusters of blocks, etc. And users define the shape of this hierarchy, and then they explicitly program. In CUDA tile, the unit of execution is a block. A block is a group of threads or execution resources that has a single logical thread of control. You write tile kernels that are executed by many blocks at once, but each block only executes the kernel once on the control thread. In the SIMD model, the grid and the block are physical. In the tile model, the grid and blocks are logical. So in SIMD, the unit of data is individual elements. You write scalar operations on elements that each thread performs, because each thread is very weak relative to a CPU thread. You wouldn't want to invoke an operation on an entire array. If you needed to have each thread apply an operation on multiple elements, then you'd write a for loop. There's just no native array operations. On the other hand, in tile programming, all of your operations are at the block level, and everything is an array. There's no scalars in tile. You express block-wide operations on arrays that are local to the block, and we call those arrays tiles. And in fact, the tile IR instructions themselves operate solely on arrays. Scalar is just a 0D array. It's like NumPy. So when running a SIMD kernel, each thread within a block will execute the kernel. But a tile kernel is run by just a single thread per block. And within a tile kernel, we create these tiles, these special type of local arrays that you can perform array operations. And those array operations are sequential with respect to the control thread, but they may be parallelized under the hood by the system using the blocks, threads, and other execution resources. So in both SIMD and tile programming, the user is responsible for splitting the computational work into blocks and dividing the data into tiles. The key difference between SIMD and tile is who is responsible for mapping blocks and tiles onto execution resources and memory. So once you've partitioned your work and data, exposing parallelism, there are still a lot of decisions to be made. What elements of data will each thread work with? Where does each thread keep copies of those elements? We have register memory, we have shared memory, which some of you may have heard of. We have tensor memory, which probably fewer of you have heard of. There's this new thing called SPM memory. There's all these various types of memory. And then how should local copies be laid out in memory? load and store those elements from global memory. And how does each thread perform computation? So in SMPTE, the user is responsible for answering all of these questions by picking from the many tools that are available. But in Tile, the system makes these decisions, analyzing the program and selecting the best tools for the target NVIDIA architecture. You can also auto-tune to pick the correct tool. All that we have to do explicitly is parallelize by dividing the problem up into blocks and tiles. And then within each block, everything is single-threaded, and you just perform array operations on tiles. So this gives us not only performance, but also performance portability across NVIDIA architectures. So we ported some of the Flash and Fur kernels, fast multi-headed attention, and batched matmul to CUDA-Tile Python. And we can get competitive performance with the same high-level code on B200, on GB300, on RTX 5090, on DGX Spark, H100, and on A100. And these results are with zero code changes and no hand tuning for each architecture, only auto-tuned parameters were changed. With Tile, we can write portable speed-of-light code for CUDA again. So CUDA-Tile Python kernels are JIT compiled to Tile IR using an execution model that allows the code to be executed without the need for a Python interpreter or runtime, similar to Numba's no Python compilation mode, and also similar to Triton and Pallas. This kind of means that it's Python syntax, but it's not real Python. It's not the true Python object model. There's some semantic compromises here that we need to be aware of. All objects have either value or pointer semantics, like in C++, and you can't do some Pythonic things like dynamically modify types, and there's no reference counting, so you must manually manage the lifetimes of your arrays, because all of this Python code is going to be compiled down to this pure native code. So Tile is an array-oriented programming model, just like NumPy or PyTorch. And if you know how to use NumPy, if you know how to use PyTorch, then you know how to write CUDA-Tile kernels. Here's an example of softmax. It's written in the left in just straight NumPy, and in the right in CUDA-Tile. So there's two kinds of arrays in Tile programming. Global arrays are typical NumPy-like arrays that are accessible by all Tile blocks. And they're mutable. If you modify their contents, all other references to the underlying data will see the changes. They're passed in as kernel parameters or globals. And you can only perform a limited set of operations on global arrays in Tile code. Most importantly, loading from them to create Tile arrays or storing Tile arrays. Now, Tile arrays are immutable NumPy-like arrays that are local to a block. Most of the common operations that you can perform on NumPy or PyTorch arrays will be supported on Tile. But these array operations will be parallelized using the block's execution resource. However, from the perspective of the block's single-threaded control, these operations are all performed. So all of CUDA's underlying launch APIs support both SMPTE and Tile kernels. So users and frameworks don't have to care how a kernel was written, be it SMPTE or Tile, to use it. And that means you can use and integrate Tile kernels anywhere that you're using SMPTE kernels today. So in CuPy, in cuDF, PyTorch, JAX, etc. Array parameters to kernel launches can just be anything that satisfies DLPAC. So it could be a CuPy array, it could be a PyTorch tensor, it could be JAX arrays, etc. Now, we said earlier that Tile arrays are immutable and that all Tile operations return copies. Tiles have value semantics. This enables optimizations like fusion, fission, and pipelining by simplifying compiler analysis. It eliminates problems such as aliasing. Some NumPy and PyTorch array operations, such as indexing, reshaping, and transposing, those typically return references to the same underlying data, not copies when possible. In NumPy, they call them views. The Tile equivalents will always return copies, not references. And this means we have to change our thinking a little bit. So, for example, one implication of that is that assignment to the elements of a tile is ill-formed. So if you need to change the value of some of the elements, you'll need to make a new tile. And you can do this with the where operation, which takes a Boolean tile and 2 source tiles, and then returns a blended tile that has the elements from the first source when the corresponding Boolean element is true, and the element from the second source otherwise. So it's a little bit unnerving to think of tile arrays as values, because typically our intuition is that it's fine to make copies and temporaries of scalars like integers, because they're cheap to copy and because they won't always be materialized. Because they have value semantics, the compiler can eliminate unnecessary temporaries, etc. But we typically think that array copies should be avoided because they are expensive and they will always lead to an allocation and materialization. However, tile arrays are different. You should treat tile arrays as you would ints. They are cheap to copy, and they won't be materialized unnecessarily. Imagine, if you will, an architecture where all of the instructions are array operations, and all of the operands and registers are arrays. And that is essentially the tile programming model. So let's look at the load and store operations in greater detail. So each of them has 3 required parameters. Both take an array to load from and store to. Loads take the shape of the tile that should be loaded, and the shape must have the same number of dimensions as the array. Stores take a tile to store into the array. The tile must have the same number of dimensions as the array. And then finally, they take a multidimensional index. This is an index in the tile space. The tile space of a global array is the multidimensional space of tiles into that global array of a certain tile shape. So a tile index ij with shape s refers to the elements of the global array that belong to the ijth tile of that shape. Now, typically, we need each block to handle a unique subset of the input data. So ct.bid returns the multidimensional coordinates of this block in the grid. Each block has a unique set of coordinates, so they can be used to find a unique chunk of data for this block. Now, if we change our tile shape but use the same tile index, then we're going to be in a new tile space, so we will load a tile with a completely different set of values. It's important to remember the distinction between blocks, which are subgroups of threads, a unit of execution, and tiles, which are subsets of global arrays, a unit of data. A block may work with multiple different tiles with differing shapes originating from differing arrays. A great example of this is tiled matrix multiplication. So we have 2 input matrices, x of shape m by k, y of shape k by n, and then 1 output matrix, z of shape n by n. And we partition in both dimensions. So each block will compute the result for an mt by nt tile of z. But to do that, each block has to load multiple tiles from x of size mt by kt and multiple tiles from y of size kt by nt. So another way to perform loads is with views. View objects are multidimensional tile spaces. The underlying tiles could come from an array, from another tile, or by generating them. For example, array.partition returns the non-overlapping tiles of an array of a particular tile shape. So you can index a view with a tile index, which loads the tile at that index from the array. You can also store through some types of views, including this one. And this is what it would look like in C++. C++ not particularly interesting for this audience. Now, these load and store operations are just a portable abstraction over the many different ways to move memory in CUDA. So, for example, load could lower to traditional synchronous instructions that are potentially vectorized, or it could use the asynchronous thread copy instructions available in newer GPUs, allowing the memory movement to be overlapped and pipelined with compute. We could also use the new tensor memory accelerator to perform asynchronous block-wide loads and stores. So the system will pick the best option available given the constraints of the memory access pattern that you've specified and the hardware that you're running on. Now, certain compute operations like matrix multiply accumulate and are also portable abstractions over hardware, this time for tensor cores. So as we discussed earlier, NVIDIA GPUs have had tensor cores for a while, but in every generation, the structure of those tensor cores has changed, forcing users to rewrite their tensor core code. With CUDA tile, you don't have to worry about all those changes. You can write tile code once, and the system will take care of mapping it to current and future tensor core hardware. So now let's talk about tile shapes. The shape of a tile must be a constant expression, something that is either a constant or that the compiler sees comes from a constant. So in C++, you have to pass them by template parameter. In Python, we express this by annotating a parameter with CUDA.tile.constant, which makes it usable as a tile shape. Such a parameter will be constant embedded in the kernel, so all uses of it will behave as if they were replaced by the value of the parameter. At JIT compilation time, we always know the values of all the parameters, but we don't necessarily want to embed all of them, because this has a big impact on JIT compilation caching. So kernels must be JIT compiled for each different value of a constant embedded parameter. So if you change one of these parameters, then you have to re-JIT compile, even if you've already called the kernel. So if you instead use a dynamic parameter, or if you call that function again with the same type but a different value, then it will use the cached compiled kernel. So you only have to recompile for different parameter types. Now, today, each dimension of a tile must be a power of 2, but that restriction is going to be lifted in an upcoming release. So in tile programming, it's important to remember that the system decides where the tile will be stored. It could be in register memory, shared memory, tensor memory, global memory, or even in a combination of different memory kinds. The system will also decide what layout the tile will have. And this is often tied to what elements each thread will be responsible for when array operations are performed. So we've looked at a lot of DL kernels thus far, but it's not all that tile is good for. Two of my colleagues wrote an excellent little tile library for sparse matrix vector multiplication. Now, sparse linear algebra is memory bandwidth bound. It can't actually utilize tensor cores, but it still benefits from tile compiler optimizations like vectorization, pipelining, unrolling, and TMA utilization. So here's the performance of their sliced LPAC SPMV implementation on B200 compared against QSparse. And the inputs are various matrices from Matrix Market. And the tile implementation, it's just one kernel that's about 78 lines of code. The existing production implementation in QSolver is 12 separate kernels totaling around 1,000 lines. And the performance of sparse linear algebra is really sensitive to the structure of the input matrices, which is why you need so many variants for SMPTE. But with tile, it's easy to write one generic kernel and then just tune and JIT compile it for the tile size of your input matrix. And so the QSolver team is actually moving to implementing all of their algorithms in tile. And that's true kind of across the math libraries. And we implemented this real-time fluid dynamic simulation in a sparse volume with smooth particle hydrodynamics using this code. So SPH models fluid dynamics as discrete particles using nearest neighbor interactions. So in this problem, you've got a domain that's mostly empty, but there's particles present in part of it. The kernel is essentially a sparse matrix vector multiply fused with a normalization. And this is not something you could usually use QSparse for out of the box. The simulation shown here models something like a dam breaking. So in this code base, we combine together tile code and SMPTE code, leveraging existing optimized SMPTE algorithms such as cub scans and sorts to perform sparse operations that are hard to express in tile. Not everything is best expressed in tile. For some algorithms, you'd be better off with SMPTE. Now, if we wrote everything in SMPTE, we could still use those libraries for sorts and scans, but we'd have to hand optimize the rest of it. If you rethink your algorithm a bit and figure out how to map it to tile, then you can mix optimized device-side libraries with your own performance portable tile code. So you can use tile and SMPTE together in any workflow. Today, you can write and use tile and SMPTE kernels in the same source file. But in the future, you're going to be able to write hybrid kernels that use both tile and SMPTE functions. So here's a little preview of that. So this Qtile kernel loads one matrix per batch element, computes its FFT, converts the result into a log-scaled power spectrum, and then quantizes that spectrum into histogram bins. It then builds up a histogram of spectral energy, it sorts the bins by count, and computes an exclusive prefix sum over the histogram. So the output is a compact per batch summary of how spectral energy is distributed across frequency ranges. And it uses a bunch of different algorithms and libraries here. It uses cuFFT-DX to perform the FFT, and cub for the histogram sort and scan. The overhead of calls between SMPTE and tile is very low. The worst case we've seen thus far has been only 4%. But what about when we need to scale out? So here's a tile implementation of a 3D FFT. It performs, almost done. It performs an FFT with cuFFT-DX in XZ, XY, and YZ. And it exchanges data between GPUs with NVSHMEM. So tile will have native support for all of NVIDIA's multi-GPU and multi-node communication libraries. So you can write device-side multi-GPU comms. And this distributed FFT code implemented with tile, cuFFT-DX, and NVSHMEM performs as good or better than cuFFT-MP. So it's easy to customize and fuse this FFT code with other operations that you might need to perform. So Qtile is a major new addition to CUDA. It's the first time we've extended to a new programming paradigm. But SMPTE isn't going anywhere. There are some things that you simply can't express in Qtile, like implementing synchronization algorithms where threads within a block must explicitly communicate. Qtile is an addition, not a replacement. But we're very excited about the possibilities that Qtile unlocks. It will now be a lot easier to write speed-of-light GPU kernels. You can see more examples of Qtile in TileGem, our open source CUDA tile kernel library. And if you want to learn more about GPU programming, there's a ton of great talks on GTC at GTC this year. There'll be a link in the next slide. We've also released this new open source CUDA curriculum that you can find on GitHub. If you have questions, you can come find me later during lunch, which I think is starting now, presumably. Okay, thank you.
So we don't have time for questions right now, but please feel free to discuss whatever you want to discuss with him. And then in 10 minutes, we have our next talk.
Oh, okay, lunch is now. I'm a second.
We request for some patience. We are having some technical problems, but we'll be starting in 2 minutes, tops. Apologies for the delay. Now we are ready. Please give us a warm welcome for Inessa, and she will be talking about control plus all plus contribute, bringing open source into the classroom.
I'll take it. Thank you. Thank you, Vasu. Thank you, everyone, for being here. My name is Inessa. Inessa Posson. I lead open source program at Open Teams. We are a US-based company distributed globally. And I'm also an active contributor to the scientific Python ecosystem. I serve on the NumPy Steering Council, and I am on the PyOpenSci advisory board. And I also maintain several repos across these communities. And in fall 2025, I also had a wonderful opportunity to serve as guest faculty for the University of Connecticut School of Mechanical, Aerospace, and Manufacturing. Through that, we ran an education experiment to make open source contributor development an intentional part of higher education. And before I share our journey and surprises and lessons learned, I would like to give a shout out to my co-presenters who couldn't join me in Krakow. Ryan Cooper is the professor of mechanical engineering at the University of Connecticut. Ryan Curtin is one of the core maintainers of MLPAC, the project that was one of the partners on this journey. And also our wonderful student, Mohamed Mundivala, who shared his learning experience with us as part of the class that we piloted at the University of Connecticut. Much of the scientific Python ecosystem originated in academia. If you took some time to learn the origin story of NumPy, SciPy, and scikit-learn, and many other libraries that we consider foundational, I'm sure many of you have used before, or at least heard of, then it all has, all libraries have roots in academia. Usually the origin story goes like this: I did the research, I needed software, I didn't want to work with MATLAB, I wrote code with Python to create a version, of sort of a version of MATLAB for what I needed to do with my research, and I realized I enjoy coding more than research. And there are dozens and dozens of stories like that. If you look nowadays, especially if you look closely to academic institutions in the US, this is like where my research is based, and then what you will find out is that some of the research still with open source still happens in academia, some of it doesn't happen, and then most of the open source development that happens during the round of a grant usually dies after. And there are hundreds, maybe even thousands of these kind of projects that go nowhere because sustainability was never considered or considered in earnest when these projects originated. And then also we can agree, those who work in academia, that the incentives of academia do not align with maintaining open source software. So for more than 20 years, many scientific Python projects now are reaching what I call inflection point. The maintainers who build these communities are beginning to step back. The pool of experienced contributors prepared to take on maintainer responsibilities remains very small. And building this pipeline is a time-consuming, long-term endeavor that's very hard to fund. And at the same time, open source offers a uniquely rich learning environment, one that develops not only technical skills, but also communication and collaboration skills with large, diverse groups of people. So together, these two perspectives led me to a question: how can we make open source a first-class learning experience rather than something students discover by accident? And I started to look for answers and collaborators. And last year, at the American version of EuroSciPy that was hosted in Tacoma, Washington, I ran into Ryan Cooper, who was one of the contributors to NumPy through Google's season of Docs, and now Sunset. And I ran this idea by him. He got really excited. He's been an advocate for adoption of open source in academia ever since his engagement with us in 2020. And with some persistence and a lot of bureaucracy, we were able to pilot an elective course for grad students at the University of Connecticut on contributing to open source. So how was it different from other courses that the students had access to? Because it's elective, it's America. Don't forget that American students usually pay for their classes. So what stood out to students that they decided to commit funding that they have available, but also time in grad school to sign up for our course? Rather than centering the course around the lectures or hypothetical programming exercises, students spend an entire semester participating in active scientific development, software development. And the course had 3 learning outcomes: to build transferable professional skills. And very often, if you're an educator, you will see that this line usually put in at the bottom and kind of like nice to have. And in reality, this is a very important outcome, learning outcome. The second outcome was to communicate technical information effectively, something that maybe not practiced enough, if at all, for many classes related to computer science and software engineering, and to develop future open source contributors. And this comes with a caveat. Somebody who's been working with newcomers and active contributors to open source for quite some time, it's a journey. It doesn't happen over a semester. But this was an opportunity for us to onboard newcomers the right way and onboard the newcomers to the projects that align with their research and their personal interests. And the broader objective was to help students understand how scientific software is developed collaboratively, iteratively, publicly, and often by volunteers working across institutions and organizations and continents. And let's touch a little more on how traditional learning happens. So it served okay for many decades. It teaches analytical thinking, technical foundations, and disciplinary knowledge. However, as Shinsky and Tanner argue, traditional assessment often emphasizes individual performance measured through exams and assignments. And these approaches tell us whether students understand concepts and if they have a good memory, but they tell us very little about students being able to navigate a large code base, understanding software architecture, or even collaborate with other people. And these are precisely the skills that define modern scientific software development. The classroom and the workplace become inherently different environments. And there's a bit of a transition for every recent graduate if they were not fortunate to secure internship, which is pretty hard nowadays, at least for American students. So this course was trying to address this gap. And I'm sharing this meme that maybe some of you already seen, but I'm sure you've had these conversations with your peer network. Is that when you are a student and you're looking for your first job, that you need work experience, but where do you get it from? And you will be that student that attended hundreds of lectures and invested hundreds of hours studying, and yet it's hard to get a job, your first job. I also wanted to bring up something that was discussed a century ago by John Dewey, and that is that education is not preparation for life, it's life itself, and this philosophy strongly influenced the design of this course. Authentic learning emerges when students encounter genuine uncertainty. Not problems with predetermined solutions, but questions where the outcome is unknown. And the open source communities naturally create these environments. Students inherit existing code, they negotiate design decisions, they receive feedback from experienced maintainers. Sometimes they succeed immediately, and sometimes they discover that software development is, in fact, a highly effective mechanism for teaching humility. And both outcomes are educational. What matters is that students become participants rather than observers. Creating this course required considerably more coordination than assigning GitHub issues. The education experience began long before students wrote their first line of code or documentation. They met with the mentors that we aligned for them from the projects that were open to the idea of this experiment, behind this experiment. And throughout the semester, they attended community meetings, worked independently, presented 7 progress updates to the class, and concluded with structured exit interviews. And this is something important to point out, that for us it was not about PRs or generating more code. It was about them learning how to join an open source community and how to become an active contributor. These are the projects that participated in our pilot, and like some of them hopefully look familiar. They represent various scientific domains: machine learning, neuroscience, numerical computing, bioinformatics, data compression, scientific visualization, different governance models, different dependencies, different contribution practices. And this is something that was discussed during our things throughout the semester, is that open source is not a homogeneous community. Just like any society, there are groups, subgroups, and it's very important to learn the rules of engagement and like speak the dialect of the community that you're participating. And this is something that I would like also to share with you, something that I developed through my work with newcomers and in the open source community, that people don't wake up one morning and decide to become active contributors. It's a journey for everyone. It happens at a different pace, but we all start with awareness of existence and importance of open source, and then we become users, and hopefully at some point we engage with the community, and I think it's becoming more and more important because code is becoming a commodity. So then how do you become a useful member of the open source community? You need to engage with the community, and you need to understand the best practices of contributing and also the needs of the project. So our goal was not to move every student to the end of the pipeline in one semester. That would be unrealistic. Instead, we wanted every student to take a meaningful next step. And in the slide, you can see how our students progressed. We had 12 students in total. None of them made to the maintainership. That would take longer than a semester, but some of them merged multiple PRs with features. And I see that my time is up, so I'm just going to, I guess, come and talk to me about the case study. The technical hiccup took up some of my presentation time, and I would like to share the story of Mohammed and his contributions, but I guess the time. Thank you. 2 minutes. I'll try to fly through this. So one case study that I would like to share is the story of Mohammed, who contributed to MLPAC. It's a C++ library for machine learning. And he worked very closely with mentors. He learned the development environment, engaged with the community, and eventually undertook the implementation of empirical mode decomposition in C++. That was a substantial challenge for him because he had no software engineering background. His background is in sustainable manufacturing. And this is an interest he had. And he just leaned in throughout the semester. He had a wonderful mentor, Ryan Curtin, and together they were able to get Mohammed's contributions to become a feature in MLPAC. And what was also interesting is that the course was a semester, but because of the close alignment of his the use of MLPAC in his research. He is continuing to work with the MLPAC community, and also not only he contributes to MLPAC, but also the lab that he's associated with, also now including faculty, are also now contributing to MLPAC, and a funding opportunity emerged. We're looking at the multi-year collaboration now, which I personally never expected when we started this conversation. So this is a very neat story that I am very excited to share. And then when it comes to experience outcomes, every project looked different. And as you could tell on the slide earlier, that every student hit a different milestone. Not everybody got very far, but everybody joined the community and learned how to set up a development environment. Everybody learned how to use GitHub, and this is something that maybe for you is second nature. It is for me. It's tool I use every day, but for many students in academia, this is something they don't get to learn because they're not taught. And also, all of them learn how to communicate on the projects that they're working on. So technical communication skills were developed by all students. They all gave presentations and taught tutorials to their peers and sometimes to faculty. Also, something that I pointed out at the beginning, the transferable skills. And I think this is the biggest outcome of this course is even if they do not continue engaging with the open source community, these are the skills that they can take to any workplace they go. And I will wrap up. Was thanking our students who took a chance on this course, our mentors and maintainers who found the bandwidth to mentor our students, and to the University of Connecticut who gave us a chance to run this experiment.
Thank you so much, Inessa, for such a wonderful presentation. Since we started late, so we are also ending late. Please maybe ask one question, and then if you have more questions, please find her. Yeah.
Hi, thanks for a great talk. So that was actually a talk where like each slide was interesting. That's rare even for a talk I've seen. So one question. So my computer science degree is like 30 years ago, and so what we did at the time was we had a couple of programming exercises during the semesters and like a final year project and something like this. Would you say that this could be generalized, and like you could say that instead of having students produce software that eventually no one's going to use, that's just educational, have them rather do something like contribute to open source, have them do that even as a final year project, so as exercises, as final year project, as like computer science diploma accompanying, so to get out of this, you produce software, no one's going to use it, into something that you've actually done something in your studies.
That's a great question, and I did think about it. I think in the ideal world, it would be the best way for students to apply the knowledge, the foundation knowledge. In a way, it's like a form of apprenticeship. So the challenge with scaling this model is finding mentors who have the bandwidth to review code and onboard contributors in all the ways that it takes to onboard somebody to an open source community. But in a world where there are plenty of mentors, that would be the best model, in my mind.
How many students did you have in your course?
12.
12. I suspect, though, that